Welcome back to the third and final video for week 5 in weather and climate. So this video is going to be more about precipitation processes. So this will include collision and coalescence, the ice crystal process, we'll go into cloud seeding a little bit, and also precipitation types. So let's get started. All right, so there are two ways that precipitation can form in clouds. One is going to be in the warm clouds, and the other one's going to be in cold clouds. And remember, when we're talking about clouds, the temperature of, or the level of the cloud is going to determine whether it's a warm cloud or a cold cloud, and whether it's mainly going to be consist of like ice crystals, or if the other one's going to be consisting of more water droplets. So warm clouds will be consisting more of water droplets, and cold clouds of ice crystals. So you can see that, warm cloud is going to create precipitation from the collision and coalescence process, and cold clouds are going to create snow, or freezing rain, or whatever it might be from up there, from the bergeron and the ice crystal process. So first we'll go over collision and coalescence. Remember, some cloud droplets must be larger than others. They're not all going to be exactly the same size. Certain materials are going to be hygroscopic and they'll be attracting water vapor, and some other, it just is the way it is. Like, some of them will just be, larger than others. And larger droplets will actually have less drag and they'll fall faster. So these larger droplets collide with smaller droplets and merge. That's going to be the process of coalescence. Now, remember, collision, when they actually run into each other, that does not actually guarantee coalescence. It's determined by the angle that they, fall at, and how big they are, and a couple different factors. And also their charges. So droplets with opposite charges are more likely to coalesce, because they attract, right? Okay, so you can see how we have in this picture of A here, we've got these small cloud droplets, and then B, we have larger cloud droplets with smaller cloud droplets. Now these are going to be falling. This is, it's motion, right? It's like it's falling down, and you can see that it's running into some of these small droplets. So some of them, that are directly below it will coalesce into the larger water droplet. Some are actually going to be more, attracted to it, depending on, like we said, what the cloud condensation nuclei is made of, or what their charges are, different things like that. And some of them are just going to bounce off, and they're not actually going to go into this larger water droplet or raindrop. Now, updrafts also will determine the droplet size as well, because it depends on if, this water droplet was just to fall from here, it's going to be one size. But if another cloud droplet is actually brought in to the cloud, or like sucked into it, and then it goes all the way through, like all the way up and then all the way down again, then it has the potential to be even larger. So these stronger updrafts permit the droplet to be in the cloud longer, because it's going to go up higher and it's going to be sucked in from down lower. So those can actually be larger. And remember, once the fall velocity exceeds the cloud updraft, so once it's falling faster than the updraft is going, up, then it's going to continue to grow and it'll fall out. Yeah. Okay. Now, like we said, the droplet growth in warm clouds is going to depend on the range of droplet sizes, how thick that cloud is, so how much time it's actually going to reside in the cloud, the updraft, so how fast the velocity is, because remember, it depends on how fast it's falling as to how, if it'll actually drop out or not, and also the electric charge of the drops. Okay, so now we'll go into the bergeron, or the ice crystal process. This is going to be in those cold clouds. So both ice crystals and liquid droplets must exist at temperatures below freezing. Okay, so we're going to have basically ice crystals, and we're going to have super cooled liquid droplets, but both of them have to be below freezing. The liquid droplets at sub-freezing temperatures are super cold, like we just said. So at temperatures above -4 degrees Fahrenheit, liquid droplets still greatly outnumber ice crystals. So regardless of the situation or the word, like, as long as the temperature is above -4, there's going to be more super cold droplets than there is going to be ice crystals. So the ice crystals actually are going to need nuclei, but instead of calling them condensation nuclei, we're going to call them ice nuclei because they help to form ice. And there's going to be less ice nuclei than there's going to be CCN. All right. The Bergeron ice crystal process is going to have a different way of forming basically ice crystals. So we have a situation where we have liquid water vapor, or liquid water droplets, I'm sorry, and an ice crystal. So the air is going to be saturated, but there's more water vapor molecules. Well, there's basically water vapor molecules surrounding the liquid. What's going to happen is, those water vapor molecules are going to be more attracted to the ice crystal, and so they're going to move from this liquid water droplet over to the ice crystal at the expense of the liquid water droplet. So that's why there has to be, a lot more liquid water droplets than there are ice crystals, because it'll just keep growing because it's going to attract more and more of this water vapor from the liquid water droplet over. And once it gets heavy enough, it's going to start falling, and it's going to fall on top of other ice crystals and also on top of other water droplets, and then that's going to actually be brought into it and make it larger. So this is going to kind of show you the ice crystals grow larger at the expense of the surrounding water droplet. So here's basically how this water droplet is, and here's our ice crystal. They're going to move from the water droplet over to the ice crystal, and then the water droplet actually gets smaller. So you can see how it's kind of moving over, and then the ice crystal is actually going to get larger. So that's how the process happens. It actually is going to take the water droplets from water from the water droplet, and it's gonna make itself grow larger. Okay, so that kind of brings us also to a thing called cloud seeding, and this is the idea to inject clouds with small particles that act as ice nuclei. So ice crystals will grow large enough to form rain. Now, you need cloud, you need super cold water, and a low amount of ice crystals. We also need effective ice nuclei, such as a silver iodide. This is actually a thing. We actually, sorry, by we I mean the United States, tried actually doing this during the Vietnam War. And after the Vietnam War, the United Nations decided that it actually was illegal for any country to use weather as warfare. The basic idea was that they would seed the clouds, cause it to rain in Vietnam, and then it would be more difficult for them to move their equipment and their things around because it would be all muddy for them. They called this whole campaign "Make Mud Not War." That's why this is down here. So you can look it up. It's kind of interesting, the things that happen, and this is something I know China is doing. There's areas of China that would be good for them to be able to grow crops. I actually was just reading something that Indonesia is working on doing that as well, because they're having a lot of flooding. So to try and stop the flooding, because they're going to make it basically rain before the cloud gets over to them, so that all the rain is all the moisture is like basically brought out of the cloud before it even gets to them. So this is something that they are doing. The thing is, and this is true for all weather, there really isn't any way to have a control. So we don't really know how this cloud seeding is actually affecting what's going on. We can't tell, would it have rained, would it not have rained, is it raining more, is it raining less? We don't know these things because there's no way to have a control to understand, how introducing this silver iodide or whatever they're using as ice nuclei, into the cloud to see if it actually, how it's affecting the cloud and the rain. Okay, and these are just a couple links I showed in my live class here. Okay, so this is kind of an idea of like how cloud seeding works. But this is actually not going to be, anthropogenic. This is going to be natural because there are natural cloud seeding. This is going to be downwind of a mountain chain, and I showed you guys how there's those those clouds that form, right in those waves here. So you can see that these cirrus clouds, because they're really far up in the atmosphere, form, and they go through the ice crystal, the Bergeron process, and ice crystals are falling. And then those ice crystals actually work as cloud condensation nuclei in something that's, low, like a stratocumulus cloud that's lower, or maybe altocumulus, that's lower down in like closer to the ground, and then that's going to cause snow to form and then fall from there. So you can see how this kind of actually would affect things too. Okay, so to go over a couple of precipitation types, we have rain, we have snow, sleet, freezing rain, and hail. We have non-frozen precipitation, which would be rain or a drizzle or a virga or a rain shower. This is all rain basically, but it depends, on the size. So rain drops that are over 0.5 millimeter, or a drizzle is less than 0.5 millimeter. I know in Nebraska we get these big raindrops because we get these huge thunderstorms. That to me would be more of a rain, where around here I've seen more drizzle, this fine kind of rain that you'll see here in the Bay. And Virga is actually going to be something I've seen from afar many times. You can see how it would be raining like further away if you're like driving down, I guess, the highway, and you kind of can see these clouds, and you can see kind of how rain's coming down, but it's not actually hitting the ground. That's because it's entering a dry layer, and then that rain actually evaporates. So it's raining higher up, but it's just not reaching the ground. And then a rain shower is where drops initially suspended by an updraft fall when the updraft weakens. So it's kind of like it's cold. The rain showers are colder because they're up in that updraft, and it's cold up there. So that's what a rain shower is. Now we also have snow, where most precipitation in the middle latitudes begins as snow, even during the summer. So this melts into rain during the summer and can reach the ground as snow in the winter. So snow can fall at temperatures slightly above freezing. So it can actually be, 34, 37 degrees, and it'll still snow outside. It's the best snow actually when it's the warmer, because you can go outside and play in it. Frozen precipitation takes up more space than liquid. So as a general rule, 10 inches of snow is going to equal 1 inch of rain. Now, it depends on if it's a wet snow or a dry snow and a couple other things, but on average, it's going to be 10 inches of snow to 1 inch of rain, which is why it's really hard to predict, snowfall amounts at times, because we're only talking about a small amount of liquid that's actually in the atmosphere, and it can produce, 6 inches of snow, or, a foot of snow or something. So it's not, it rains commonly, like during the springtime, 3 inches, overnight. So that's like, 3 inches of rain isn't that much really, but that would equal 30 inches of snow if it was the equivalent. So, okay, so that brings us to actually sleet and freezing rain. So we'll go over sleet first. Sleet is where there's a strong temperature inversion present. So basically we have snowflakes. See, this is colder. Here's our vertical profile here. It's going to show us the temperature, right? So you're going to have this snowflake that's going to fall, and it's going to be warmer and warmer and warmer until it hits above freezing, this point in the middle here. Okay, the snowflake is going to melt at that point because it'll be above freezing, until it hits a point where it starts getting colder again, and then it reaches a point closer to the surface that's actually freezing again. And so then that raindrop is going to freeze, and it's going to fall as sleet. So it falls as snow. It enters an area of the atmosphere that's above freezing, so that snow melts into a raindrop. And then it enters another area where it freezes, and then that raindrop is going to freeze as sleet. Now, I think I have a picture. Yeah, I was going to say, sleet falls as like little itty bitty pebbles. It's kind of crazy how they look, actually. And it can look like snow sometimes if there's enough of it. It can look like let's see. Yeah, I don't really have any more pictures of it. But this is basically what it's going to look like. They're just kind of like little itty bitty pebbles, because these are basically all little individual raindrops that have frozen into sleet. That's sleet. But the other thing that we're going to go over is actually freezing rain. And here's a picture of freezing rain. You can see the freezing rain and sleet do not look the same, although they form on almost identical atmospheres. I can tell you that freezing rain is really, really dangerous. So meteorologists really want to try and warn people when these events could potentially happen. If you see how this is frozen onto a a branch here, it gets really, really heavy. And if there's leaves, still on the trees, this happened in Omaha in like 1997. It was like a freezing rain slash snow event, and it just took all the branches out of the trees and took all the power lines down. And gosh, we went out without power for like 3 weeks because everybody was without power. But more than that, losing power and all that. If you could imagine, this layer of ice is also on everything, including the streets and the sidewalks. And I mean, it's super slippery for cars to be driving around, super slippery for people to be walking on and potentially falling and, harming themselves, having to go to the hospital, that kind of thing. These storms could be really detrimental to communities. Um, so let's look at what the back to back here. So this one is going to be freezing rain, and this is going to be sleet. So remember we said it fell as snow. It entered an area here that made that snow melt into rain, and then it entered a colder area here that made that rain refreeze into a pebble called sleet. Now, freezing rain has almost identical vertical profile, but the difference is that this layer, the area that it enters to refreeze again, closer to the surface, is not going to be as deep. It'll be really shallow. So there's not enough of time for the raindrop to fully freeze into sleet. So what it does is it becomes super cooled. So it falls as snow, it enters an area of the atmosphere that's warmer, and that snow melts into rain, and then it enters an area that's colder right before it hits the surface, just enough to make it super cooled. And when something super cold hits something, like hits a surface, then it freezes on contact. It's like those guys that take those bottles of water out of the freezers on YouTube. You can see them smacking the bottle of water and then it completely freezes or turns into slush. It's like that same idea. So we've got this raindrop that's super cooled, and as soon as it hits the surface, it just freezes. Really dangerous stuff. Okay, and then I think this is the last one we have here is hail. Hail is formed completely differently than sleet, even though it can look the same from the outside at times. It is definitely not the same on the inside, and it's not formed the same at all. So hail is actually formed by an updraft. It's a raindrop that gets sucked up into an updraft. And this is a thunderstorm, so a cumulonimbus cloud. Okay, it gets sucked up and it goes above the freezing level of the cloud and it freezes. Okay, and then it falls and it goes below the freezing level, and so it melts a little bit, picks up maybe some more water droplets, and then it gets picked back up by the updraft, because in a cumulonimbus cloud, the updraft is really strong. There's a lot of circulation going on. And so then it goes above the freezing level again and it refreezes, and it just keeps going around and around and around inside this cloud until it eventually gets so heavy that updraft can't support it anymore and it falls out. Now, if you split open a piece of hail, there's actually layers to it, and the reason why it has layers is because of that circulation that it goes through, where it melts and then refreezes and then, picks up more water and melts and then refreezes. And how large a hailstone can get is going to be directly determined by the strength of the updraft. So when I've been chasing storms before, I've seen hail that's this big. I've literally got out of my car and picked one up, and they've been this big. Can you imagine the strength of an updraft to be able to support a piece of hail that's that big? They're pretty heavy. So there's a lot of force going on inside these cumulonimbus clouds. But that's how hail is formed. So the largest recorded hailstone, this has actually been beat last year. I need to update my slides. But before last year, it fell in Aurora, Nebraska. Nice little town. I've been chasing there a few different times. It has a really nice free campground in it. But the largest hail was about the size of a soccer ball. If that thing hit you in the head, it would really cause you some damage. So hailstorms is no fun to get stuck outside in. It's best to take shelter. It can damage lots of property. There was a hailstorm that went through Nebraska and hit an area that had a lot of used cars for sale. It's kind of known in the Omaha area to be the part where everybody goes to buy cars. Anyway, it hit that area, and it was like thousands of cars were were completely demolished because of the hail. I mean, and it was hail like grapefruit size hail that fell on those cars. So hail is no joke. All right, so here's the group questions. This is the last of the videos for the week. I hope you guys have a great week, and we have a test upcoming next week. I will email you guys more regarding that.